Hello, everyone. I'm Losey. I'm a postdoctoral scholar at Stanford University, and I'm really excited to be a part of this workshop on interactive robot learning. Today, I want to present some work that myself and collaborators in the ILLiad lab have been doing over the last 9 months or so on personalizing robots through learned latent actions. This idea of personalization is very near and dear to me. I'm excited about developing robots that can leave factories, leave labs, and go out into the world. And of course, in the world, they're going to run into all different types of people. People have different preferences, different wants, different needs. And so it's not enough to make a sort of one-size-fits-all algorithm. Instead, we need robots that can adapt, embrace our differences, and personalize to different users. One application that I have in mind when thinking of personalization is assistive robots, such as the one you see on the left. This is a wheelchair-mounted robotic arm. There are almost 1 million American adults living with physical disabilities that, because of these disabilities, struggle to perform everyday tasks, such as eating or going to the bathroom. Physically assisted devices, such as this wheelchair-mounted robotic arm, are one way that we can help these people regain autonomy and improve their quality of life. So here's a video of someone using their wheelchair-mounted robotic arm around the house to do everyday tasks, opening the fridge, grabbing things from the shelf, or opening a door. You'll notice that they're controlling this robot arm using a joystick on the bottom right. The robot arm itself is dexterous. It has 7 degrees of freedom. And if we only think about the end effector, we need to deal with the position and the orientation. But this joystick is only 2 degrees of freedom. I can only press up, down, and left, right. And so to overcome this fundamental disparity between the high-dimensional robot arm and the low-dimensional input, right now the person is pressing a button to change between modes. So that in one mode, they control the robot moving in a plane, in another mode, they control moving up and down, and so on. Assistive robot arms are useful because they're dexterous. This dexterity enables the user to perform complex tasks. But it's also a burden, because it's challenging for users to control these very complex robots with a low-dimensional input. In fact, under current strategies, users spend up to 20% of their time just switching between modes, pressing that button to figure out how they should be controlling the robot. And that prevents them from actually doing the fundamental tasks that they wanted to do, like eating or going to the bathroom. And so what we're arguing is that we can learn a personalized control strategy in order to enable more intuitive control of these dexterous robot arms. I want to show you guys a vision of how this could work. We imagine collecting offline, personalized demonstration of high-dimensional robot motions. Here I'm providing those demonstrations through kinesthetic demonstration. We can also imagine them being provided by a caretaker, or even by just controlling the robot using the joystick as it currently is done. Next, I'm going to embed those high-dimensional actions into a low-dimensional latent space, which I'm then going to give to the user to control the robot. Here, one dimension of that latent space causes the robot to move across the table, and the other dimension causes the robot to perform a pouring motion. So overall, the big picture idea is that we want to make it easier to control high-dimensional robots by embedding the robot's actions into a low-dimensional latent space. There are a few different properties that we want this latent space to have in order for it to be intuitive to users. The first one, and the one that I like the most, is conditioning. Imagine that you're using this latent space to, let's say, pick up a glass of water. Maybe pressing up on the joystick brings that glass of water to your mouth. And that makes sense. What happens when you're in a different context? For instance, grabbing a doorknob. Pressing up on the joystick shouldn't bring the doorknob to your mouth. In fact, the way that the robot interprets your inputs should depend on the context that it's currently in. And that's exactly what this equation is saying. Here, A hat is the reconstruction of the high-dimensional robot actions. That's what the robot's actually going to do. Phi is our decoder, and Z is the low-dimensional latent input. For instance, this could be 2 degrees of freedom like a joystick. S is the state. That's the context that the robot's currently in. And what this equation argues is the way that the system decodes my inputs should depend on both Z, the latent input, as well as S, the context. The second property that we want these systems to have is that they should be controllable. Now, recall that when we're training these systems, we provide demonstrations, showing them different tasks and skills. We want to make sure that the user can recover all these different skills that we showed at training time at test time. So for example, imagine that you're given a start and goal state that were originally in the data set. We're arguing that there should exist some latent input Z, or perhaps a sequence of latent input Z, so that you can move from the start state to the goal state. The third property that we want the system to have in order to be useful for people is we think it should be consistent. I also really like this property. I find it intuitive. Imagine that you're controlling this robot and you're pressing right, and that's causing the robot, let's say, to bring this glass of water to your mouth. The robot shouldn't, if you continue pressing right, the robot shouldn't bring it to your mouth and then suddenly put it back down and then maybe move it off to the side. Instead, when you provide the same Z, the robot should behave similarly in nearby states. And that's exactly what we're capturing here. The last property that kind of builds on the one before is scalability. The idea being here that if you provide larger latent actions, the robot's actual behavior in the world should cause larger changes. If we tie together these last three properties, controllability, consistency, and scalability, there are close connections with Lipschitz continuity in this latent space. So we've got these four properties that we want the robot to learn and want the robot to have in order for it to be user-friendly. How do we capture those properties and learn a latent space? We tried a few different models. Of course, one naive baseline would just be principal component analysis. What we found to be most effective was a conditional variational autoencoder, shown here. We first collect our data set of state action pairs on the left. We then embed these high dimensional actions into a low dimensional latent space, Z. Then we try to decode that lower dimensional input Z based on the state or context S to finally reconstruct an action A hat. Ideally, A hat will be very similar to A, so the robot can recognize this is actually the complex high dimensional action that you wanted me to take. Then we can remove the encoder and let the user control the system. They'll provide some sort of joystick inputs which will directly map to the latent space Z. The robot will then take these low dimensional inputs and, based on the context, decode them to high dimensional actions that are useful in the world. Let's kind of see how this works in a simulation. This is a 5 degree of freedom planar robot, and we've shown it how to move left and right along a sine wave. And if you think about it, moving left and right, that's only a 1 degree of freedom task. So I shouldn't need to control all 5 degrees of freedom of this robot separately. The first property that I want to talk about is scalability. The idea being that as I press more left, the robot should move more to the left. And as I press more right, the robot should move more to the right. And that's exactly what we're seeing here. The second property I want to touch on is consistency. Sure, the robot knows to move left and right at one state, but what happens at all the other states? Does left mean left all the way across this sine wave? Well, when we learned the latent space using this autoencoder, that's exactly what we found. At each of these different states, pressing left does cause the robot to move left. Okay, great. So we've got scalability, we've got consistency. What about the first two properties? Well, let's look at one more simulation. Here, we've got the robot arm, and it's kind of starting off the sine wave. And all I'm going to do to control this robot is I'm just going to press and hold right. I'm just going to try to get the robot to move to the right. One naive approach for controlling this robot would be something kind of similar to PCA, where we don't condition our interpretation of these inputs on the state. And when we don't use the state conditioning, the robot does learn to move to the right, but it's not accurate at all. It's not following the sine wave. Introducing this state conditioning is key for causing the robot to actually perform the task correctly and follow the sine wave. This ultimately gives us this property of controllability we want, because now I can move the robot along the sine wave between any sort of start and goal states I want to achieve. Okay, great. So kind of that simulation hopefully demonstrated the 4 properties that we want. Let's look and see how this actually works in a user study. We're going to perform a user study that's based on a cooking task. We trained the robot with about 7 minutes of kinesthetic demonstrations. These demonstrations showed skills that were relevant to the overall cooking task, but didn't perform the task entirely. There were things like moving between shelves, pouring, stirring, reaching, basic skills that we might need when cooking. We then compared 2 different strategies. First, our latent action approach that we've just been discussing, and second, the current method that's being used for assistive robots. This is going to be the end effector approach. You might remember this approach from the video at the beginning of the talk. There are different modes, and the user toggles between those modes by pressing a button. Here, one mode is going to be a linear controller, where the person controls the X, Y, and Z position of the end effector. And the other mode will be an angular controller, where the user directly controls the roll, pitch, and yaw of the end effector. We contrast this to our approach, this latent action method, where the user only ever has one joystick, and they can just press up, down, left, right. So let's see how that worked. Remember, this is a cooking task where we had kind of a toy goal of making apple pie. On the left, we're going to show the end effector mode, and on the right, our latent action approach. All videos are shown at 3 times speed. Here are the users doing the very beginning of this apple pie. They're going to pick up eggs, pour them into the bowl, and then drop the container into the recycling bin. You'll notice on the right, with the latent action approach, they're already off and running, almost complete with the task, whereas on the left, with end effector, they're lagging behind. We saw this pattern across the different users, where regardless of who it was, they were able to complete the task more quickly using our approach. Of course, we tried different tasks as well. Here's another part of this making an apple pie, where now we're trying to grab the flour, pour the flour into the bowl, and then return the container to the shelf. We didn't provide users with practice time with either method. They sat down and immediately started performing the task with either end effector or latent actions. We counterbalanced the order of presentation so that half the users started with the latent action approach and half started with end effector. You'll notice that this user is very stuck when using the end effector method. Finally, we also tried moving things around in the world. Because the conditional variational autoencoder is conditioned on the state, changing the state itself shouldn't really matter. The robot should still be able to recognize what actions it should take. Here you're going to see the full task of making an apple pie. And we've kind of moved where the recycling bin is, where the shelf is, etc. This is shown at 4 times speed. This user has already successfully dropped the eggs in the bowl and is moving on to the flour, whereas on the left with end effector, they're kind of stuck at the beginning of the task. One kind of fun thing about this is that people were able to control the robot to do these tasks in different ways, or even to do slightly different tasks, because they were given control of the robot. They could use this latent space to do different things they wanted to in the world. One other fun thing is, for example, stirring was done very differently by different users. This user sort of mashed, other users would use stirring in a circle, etc. Okay, so to summarize this part of the talk, we're excited about assistive robot arms because they're dexterous. They can do these complex things, but the dexterity is also a burden because it kind of makes it hard for people to control these robots. So what we did is that we proposed we can embed high dimensional actions into a low dimensional latent space. We're going to learn this latent space directly from data and then give it to a user. In order to make sure that it's intuitive to that user, we tried to capture 4 different properties that we wanted it to have. We then trained these latent spaces based on what I would consider to be an efficient amount of data, about 7 minutes of kinesthetic demonstrations, and then performed this cooking task where people were able to make an apple pie using the latent space. So in this first half of the talk, we were correctly able to learn the latent actions, and we saw how these latent actions could be useful. They could enable personalized low-dimensional control. But is that enough? Is it enough for us just to use latent actions if we need to do precise manipulation tasks? For example, eating. Here you can see someone controlling their assistive robot arm to try to grab different orange slices. You'll notice how precisely they have to manipulate this robot to get directly above the orange slice they want before stabbing down. We tried doing the same thing with our latent action approach by itself, nothing else. Here are the users trying to stab a marshmallow that they want to grab. You'll notice how much time they spend trying to line this up, and they still miss. They weren't able to exactly get the marshmallow they wanted because of how precise the task needed to be. And that suggests that just latent actions enough maybe can't solve these more precise manipulation tasks. So our approach, or our insight, is that we can combine these learned latent actions with shared autonomy, a paradigm for assisting the user, in order to enable precise assistive manipulation for applications such as eating. So with this eating in mind, imagine that you have a plate in front of you. There are many different things you could want on the plate, but you'll notice that they're kind of discrete goals. I might want to reach for the rice, I might want to reach for the tofu, etc. Imagine that you're working with a robot to reach one of these different discrete goals. The robot starts with its gripper somewhere above the plate, and you start by controlling the robot, moving towards these different goals. At the beginning of the task, the robot has a belief, or sort of a confidence over which goal you might want to reach. Initially, let's say this belief is uniform, so that half the time the robot's like, I think you want to go to the rice, and half the time the robot believes you might want to go to the tofu. As you start actually moving the manipulator, the robot can update this belief. Here, because you're moving towards the rice, the robot updates this belief to be more confident in that the actual goal you want to achieve is the rice. And similarly, if you were to move towards the tofu, the robot could become more confident in the tofu. The idea in incorporating this belief is that it gives the robot a sense over, of these different discrete goals, of these different dishes on the plate in front of you, which one do you want? where do you want to go? And if I know where you want to go, the robot can then help you reach that goal and stay there. We argue that we can incorporate this belief within our latent action approach to improve its performance. The user provides inputs Z, and the robot sees its state S. The decoder is based simply on Z and S. We now want to suggest that the decoder should also consider its belief over these different discrete goals. So that, for example, when the robot is very confident that you want to reach the rice, its latent actions might be different, have different meanings than if the robot is very confident you want to reach the tofu. For example, the robot might know, hey, we're reaching the rice. It's really likely you might want to scoop the rice. Whereas when you're reaching the tofu, it's more likely you want to stab it. So we can sort of incorporate or unpack this to reach our overall vision. We imagine settings where the human is trying to control the robot to reach different discrete goals. Here, there are these two different cups on the table, and the robot does not know which cup the human wants to reach a priori. The human controls the robot using latent actions, and at the beginning of the task, these latent actions should control which goal the robot moves towards. But once the robot gets closer to a goal and as it sort of sees the trajectory that the user is providing, it can update its belief. It becomes more confident, hey, you want to reach this red cup. Once it has this confidence, we want to change the meaning of the latent actions along some sort of scale, so that now instead of controlling the high-level goal, they actually change your low-level preference. So again, we've moved towards this red cup, and now the user can use those latent inputs to control how they grab that cup, either from the side or from the top. They're controlling the style along a continuous spectrum or a continuous low-level manifold using the latent action approach. So when we combine shared autonomy with learned latent actions, what do we get? What are some of the properties that we have here? Well, the first one, and perhaps the most intuitive, is that if we incorporate shared autonomy, helping the robot reach and maintain these goals, the robot becomes constrained to some region about this goal. More formally, we can say that we have some convergence properties, where the robot is uniformly ultimately bounded about the human's desired goal. And the size of that bound, sort of the radius of that bounding ball, decreases as the robot becomes more confident that that's the goal you want to reach. This is a blessing because it makes sure that we reach and maintain the goals we want to achieve, but it's also a curse because what happens if I start moving the robot towards one goal and then I change my mind? With this convergence property, the robot is stuck within this ball. How can I get out of that and move back to a different goal that I might actually want? In order to enable that, we also encourage the robot to learn latent actions that have high entropy in the goal space. Intuitively, we want to make sure that the robot always has access to some latent actions that move towards different goals, even when I'm very confident that I want to reach one goal. Finally, we're able to use this learned latent space to actually generalize to goals that were never seen at training time. So I can train my latent space using a few goals, and then I can introduce a totally different goal. The reason I could then work with this totally different goal is just through a geometric transform. For example, I might learn how to work with one door, let's say in the environment. I can then look at something else, call that a door, and geometrically transform the different ways I decoded the first one to the second one. I want to emphasize the second property, which has to deal with what happens when I reach towards one goal and then change my mind. How do I make sure that there are latent actions that enable me to move between goals? So the ideal behavior is going to be shown in this video. I'm going to start off reaching towards one goal, this red cup. Once I get to that goal, I can use the latent actions to change my preference, grabbing from the side or grabbing from the top. But then I change my mind. I think, no, that's actually not the goal I want to achieve. I want to reach for this purple cup. If I learn this latent space correctly, and I have the entropy in the latent space, I'm arguing that I can then change. I can switch to this other goal. So in these plots on the right, we're going to compare two different sorts of latent spaces. One where we just focus on minimizing reconstruction loss, so that we can accurately perform the actions shown in the training set. The second one is going to be one that also encourages entropy, so that there's some disparity between these actions and being able to reach different goals. On the x-axis, you'll see time, and on the y-axis is confidence. When confidence is 0, that means the robot is sure that it should be reaching the red cup. And when confidence is 1, the robot is sure that it should be reaching the purple cup. So what happens when the human changes their mind early on in the task? So here, after 3 discrete time steps, I've changed my mind from reaching towards the red cup to now reach the purple cup. For both of these different models, with or without entropy, the robot can deal with this change and reach for the correct cup. But what happens if I change my mind a bit later on? I maybe reach all the way to the red cup and then think, no, actually, I really want to reach to the purple cup. Here you'll notice that without entropy, the robot becomes constrained to some region about this incorrect goal, and the human can, no matter what they do, they can't lead the robot away from that goal. On the right, the simulated user is actually able to guide the robot away from the wrong goal and towards that correct goal, even though the robot is very confident that this red cup is the real goal that it should be reaching at the beginning of the task. We extend this one further so that much later in the task, the human changes their mind. Here, after 9 time steps, you'll notice that when the robot doesn't incorporate entropy into latent space, it's completely stuck. There's no way to get away from the initial goal. Whereas when we have this entropy and encourage the robot to learn actions that move between these goals, the human is still able to change the robot's mind, even if it is very confident. So with this idea in mind, shared autonomy and latent actions, we did a couple of user studies, and we had some baselines that we wanted to compare to. The first baseline drawn from literature is retargeting. Now, this is a method that's pretty analogous to the end effector control we mentioned earlier, where it maps my joystick inputs to the robot's end effector motion. Of course, I pick this mapping in an efficient way. Here, I minimize the energy of that mapping so that, for example, the robot doesn't get stuck in singularities. The second baseline I want to mention is hindsight optimization, which is a state-of-the-art approach towards shared autonomy. Here, the robot maintains a belief over the discrete goals, the different objects it might want to reach, and it uses essentially a problem to determine what actions it should take given that current belief. So within our user study, where we're going to focus on an eating task, we ultimately tested 4 different conditions, where we separately varied 2 different things. First, we compared whether or not to incorporate shared autonomy. Second, we compared whether or not we should use direct control, where, for instance, I'm using my joystick to directly control the end effector robot, or our learned embedding, so that I'm using this learned latent space. So completely opposite ends of the spectrum are going to be R, which is just retargeting by itself, and then LA plus SA, which is latent actions and shared autonomy. That's our proposed approach. So let's see how this worked in an eating task. On the left, we're going to see R, retargeting, and on the right, our own approach. Here, the user is going to try to stab the marshmallow, dip that marshmallow in the icing, scoop the marshmallow through the icing, and then dip it into the rice before putting it on their plate. Throughout this whole time, they're controlling the robot using a joystick. The robot recognizes that there are 4 different goals the human might want to reach. The plate with the marshmallow, the plate with the icing, the rice, and finally, the plate that the human wants to put this assembled thing on. You'll notice that throughout this task with just retargeting, the human's almost always in the same orientation. They're kind of always holding the end effector sort of perpendicular to the table. We're calling that a stabbing orientation, and the robot is almost always perfectly aligned with the stabbing orientation. It never gets into a scooping motion when using just retargeting by itself. Now let's see how our approach works. Remember, the robot knows that there are a few different discrete goals I might want to reach towards, like stabbing the marshmallow. And once I get to those high-level goals, I can then control the low-level preferences, such as stabbing or scooping, using the latent actions. So you'll notice that the user was there able to correctly scoop into the icing to push that onto their marshmallow. Finally, they dip it in rice and put it on their plate. I want to show 2 contrasts here. First, the user was able to complete this task much more quickly when using our approach. But second, they are able to actually change their low-level preference once they reach these different goals. You'll notice that they sort of switched from a stabbing orientation to a scooping orientation when they were trying to grab the icing, which they weren't really doing when they were just using end effector control or retargeting by itself. Okay, I want to do one more experiment. This is going to be a slightly different task, but here comparing just latent actions by themselves with latent actions plus shared autonomy. Here, the user is going to try to reach for some tofu, then align the end effector so I can cut the tofu, and finally scoop the tofu onto my plate. Again, I only ever have access to one joystick, up, down, left, right, in order to control the bot to perform this entire task. With shared autonomy, the robot has no sense of goals. It doesn't recognize that, hey, staying near the tofu might be important to the user. And so this makes it really challenging for the user to really precisely control that end effector. They reach the tofu, but then as soon as they start trying to change the style, changing that low-level preference, maybe just to cut, the robot starts drifting away from their goal. They don't have any help. There's no autonomy helping assist them to maintain that goal. And so they're fluctuating throughout the task. Next, let's see what happens with our approach. Remember that here the robot knows that, hey, the tofu could be one goal the human has. And when the human reaches towards that high-level goal, the robot will use shared autonomy to constrain the user above that tofu. Then it's up to the user to control these low-level preferences, cutting from the side, scooping, etc. This makes it much easier for the human to complete the task more quickly using both latent actions and shared autonomy. Users are able to complete this task in about half the time, and for this particular user, you'll notice how they're able to change their alignment between scooping and cutting much more consistently with our approach. Overall, we conducted a Likert-Scale survey to see what people thought about each of these 4 different strategies: retargeting plus shared autonomy, latent actions, and latent actions plus shared autonomy. Remember, latent actions plus shared autonomy in orange is our proposed approach. You'll see that kind of across the board, people preferred our approach. They found it easier, more helpful. They were better able to do precise tasks. They thought it was more intuitive and overall preferred it. So we think these are some suggested results of maybe the merits of incorporating shared autonomy to help constrain the users to different goals when they're using this latent action approach. In the second half of the talk, we mentioned that latent actions are certainly effective and that they enable users to control high-dimensional systems with low-dimensional inputs. But just latent actions by themselves aren't really enough for these precise manipulation tasks. Remember Han completely missing that marshmallow when he tried to stab it. So what we did is we combined latent actions with shared autonomy, where the robot has a sense of what goals might exist and helps the user reach and maintain those goals. We then introduced the belief that the robot has over goals into the latent action approach so that the latent actions have different meanings when we're trying to reach the high-level goals, or once I reach those goals, I now can control the low-level preferences. We also introduced an entry term into the latent action approach in order to make sure that the human was able to move between different goals and they weren't trapped once the robot was very confident they wanted to reach a specific goal. Finally, we conducted a user study with 2 different eating tasks. If you want to read more about these 2 different parts of the talk, they're separated into 2 different papers. The first half of the talk summarizes this paper, Controlling Assistive Robots with Learned Latent Actions, which will be presented at ICRA this year. The second half of the talk, which introduced shared autonomy, focused on the second paper, Shared Autonomy with Learned Latent Actions. We're going to present this paper at RSS in the coming months. I'd like to thank all the different people that helped contribute to this research, especially Krishnang, Hong, Mungshi, Ajay, Animesh, and of course, Dorsa. And just to finish this talk, I want to plug where I'll be next fall. I'm currently at Stanford as a postdoc, but starting the fall, I'll be an assistant professor at Virginia Tech, where I'll be founding the co-lab. I'd love to talk to you more about this work, my lab, etc. So feel free to reach out. Thanks.